Hi everyone, I'm Xiao from Pennsylvania State University. Today I'm going to introduce optimizing fitness for use of differentially private linear queries. Differential privacy is a widely accepted mathematical definition of privacy, and it's adopted by industry and government agencies such as Bureau of Censors, Facebook, Yahoo, Google, and Apple. And it's very helpful for collecting and releasing sensitivity information. In this paper, we're going to use epsilon and delta differential privacy. It says that the neighboring data set vector x and x prime doesn't differ much on the output. We also use the L2 sensitivity, which measures the distance between two inputs. In this paper, we use the exact Gaussian mechanism, which adds an m-dimensional vector of independent Gaussian random variables to the input data. It says that the delta, as long as delta greater than this quantity, the mechanism will satisfy the epsilon delta differential privacy. Now let's take a look at the fitness for use problem. In the traditional mechanism, like matrix mechanism, they basically try to minimize the sum of variance. So for example, if we have two queries, Q1 and Q2, the algorithm may result in the variance that they are very close to each other, but they will sum up to the minimizer. However, if under the same privacy course, what if we want that Q1 is more accurate? For example, if we want to make sure that the variance of the Q1 is more than 1, while we allow more noisy answer of Q2. The traditional mechanism cannot guarantee such a constraint. So that comes our fitness for use problem. It will satisfy per query accuracy constraints. And now the problem is just how do we define this accuracy constraint formally? So the accuracy constraints here, first we have the workload matrix, which can be represented in two matrices. So first it's the base matrix, which is a bunch of a set of linear independent queries, and matrix L is the representation matrix. And the mechanism here is we add independent Gaussian noise to the base queries, and then we represent them back to answer the workload W. In this representation, we can calculate the variance of each query. It's the jth element of the diagonal of L sigma times L transpose. Finally, we can write down our accuracy constraints. So in order that each query has variance at most some Cj, which is the accuracy constraint, this inequality has to be satisfied. And then we want to measure how we define the privacy course. The theorem we have that if a mechanism satisfies epsilon delta differential privacy, it will satisfy this quantity. So delta should be greater than this term. Here, phi is the cumulative distribution function of standard Gaussian distribution. And it turns out that this quantity is increasing in delta m, and the delta m is defined as follows. So we call this delta m as the privacy course, and we want to minimize delta m so that delta is as small as possible. Now we have privacy course and accuracy constraint. We can write down our fitness for use problem. So it looks like this. This part minimizes the privacy course, and this part enforces the accuracy constraints. So this problem has two benefits. The first is that it's convex, and the second is that the solution is unique. So theoretically, it's easy to solve, but practically, the constraint optimization is hard to solve. So we need to do some modification to the original problem. So first step is we want to transform it into an unconstrained optimization problem. That's why we need to rewrite accuracy constraints. So the variance more than some targets bound, we moved it to the denominator. So it's equivalent to say that the maximum of it is more than 1. And then we can move the constraint to the objective function. So the privacy course is just the same. But the accuracy constraint, we can minimize the maximum of it, and then we can scale this sigma to make sure every term is more than 1. Now we got this approximation, this unconstrained problem, but still the gradient of max function is very hard to calculate. Then we need the second step, and we want to approximate the max function using SoftMax function. The SoftMax function is defined as follows, and the property is that when t goes to infinity, the SoftMax function converges to the max function. And finally, we come to our practical optimization problem. So the first term deals with the privacy cost, and the second term handles the accuracy constraints. Note that in the end, we need to make sure that the sigma is scaled properly. So in the end, we have this variance is more than the desired target bound. And then we propose the optimization algorithm. So there are 2 steps that is important. The first, we use the conjugate gradient method here, which can speed up the calculation. And it's also memory efficient because it doesn't require that you calculate a very large matrix. And also we use this backtrack line search method, which makes sure the sigma is positive definite. Then we come to the experiment part. We want to make sure our algorithm works well. So we have some comparing algorithms. The IP just add independent Gaussian noise to the vector. HM use a strategy matrix X to solve the matrix mechanism problem. The CA is a complex optimization solver to the matrix mechanism problem in L2 space. The version 1 is also, it changed the workload by divided the target variance. So makes some part of the queries more accurate, so more important, yeah. And the version 2 scale the query by the square root of the variance. And SM2 is our fitness for use problem algorithm. So first we calculate minimum privacy cost using SM2. Then we use the same privacy cost to measure how much each algorithm exceeds the accuracy constraints. And we use the quantity max ratio, which is defined as the maximum ratio of query variance to the target variance for each method. So we want to see if the other algorithm can satisfy these constraints. So first we have this experiment on random range queries. We first set all of these accuracy constraints to be 1, and we measure on different dimensions. So in this case, because we don't weight the workload, both 3 methods are the same, 3 versions of it are the same. And we can see that SM2 achieves like around 35% improvement on the best solver. Also in the experiment, we find that the sum of square error of SM2 is not much larger than this CA, which is the complex optimization problem solver. So it's a good balance. We also have the experiment over the random constraints. Instead of uniform constraint, we have this, where we set them sample from 1 to 10, randomly sample from 1 to 10. The results are also the same or similar. It achieves around 40% improvement. And the sum of square error is like 1.2 to 1.3 to the data of convex optimization algorithm. So we see a good example here. And finally, in this paper, we introduced the fitness for use problem. And the goal is to calculate minimum privacy cost under accuracy constraints. And then we also propose an algorithm to solve this problem. So that would be the end of this presentation. Thank you.